You have seen countless videos showing how to connect an OLED and print Hello World or something similar with ready-made libraries. But what if I told you you are missing 90% of what's really happening inside this tiny screen? How do individual pixels actually turn on? How does the SSD1306 controller interpret your data? And why do most tutorials hide these secrets behind black box libraries and slow I2C code? Following our LCD deep dive, we will now explore the OLED journey and open up the SSD1306 datasheet to really learn how an OLED works, understand SSD1306 internal architecture, draw pixels via SPI interface, and build platform independent code for ESP32 and STM32 controllers. But wait, that's not it. Once we master the basic display magic, we will level up to high level graphics. That is, to integrate LVGL graphics library on our monochrome OLED display, something most people shy away from. We will display text and images using this LVGL library. And then we will design custom UI using Squareline Studio and get it running smoothly on our SSD1306 based OLED display. By the end of this video series, you will gain the confidence to design displays your way on your terms. Namaste and welcome back to Avinashi Tech, where we don't just follow tutorials, we decode and demystify tech, build funky projects, and experiment with controllers and protocols to make things interesting. If you share the passion for embedded systems, then this channel is for you. Subscribe and let's bring those pixels to life the right way. Alright, time for the boring stuff, or as I like to call it, the part where 90% of viewers click away. If you are still here, congrats, you are in the 10%. Yay! So, the OLED display we are using is a typical 0.96-inch monochrome SSD1306 panel, one of the most common types you will find. It's called monochrome because it only sees the world in binary. Either a pixel is on or it's off, with mostly blue or white color variant. These displays usually come in two main interface variants, that is I2C and SPI. The I2C version is the simplest. It has 4 pins, 2 for supply, that is VCC and ground, 1 for I2C clock and another for data. Super easy to connect, but a bit slow if you want to do fast graphics updates. The SPI variant is faster and actually comes in two sub-variants, a 7-pin version and a 6-pin version. The 7-pin version of SPI has VCC and ground for supply, an SPI clock, SPI MOSI data pin, and SPI chip select pin. There is also a data or command pin, DC, and a reset pin. Then there's the 6-pin SPI version, which basically skips the CS pin. In this case, the chip select is permanently tied to ground on the module itself, which means you can't really use it in a proper multi-slave SPI setup. Who makes these weird configurations anyway? Apparently,
China.
And guess what? My supplier blessed me with this rare 6-pin SPI variant. Fantastic. Anyway, have you ever received a Chinese clone module with a weird configuration, but it still somehow works? Share your experience in the comments. I'd love to know that I'm not alone. Let's open up the datasheet of our main character, the SSD1306 controller manufactured by Solomon Systech. This tiny IC is the real brain behind your OLED. It handles the memory, converts data, drives the pixels, and pretty much does all the heavy lifting. So, let's zoom in and explore how it works internally. So SSD1306, it is a single chip OLED driver, and each LED on the panel represents a pixel or dot on the display. These LEDs are further connected in a common cathode configuration. This controller supports a parallel interface similar to our earlier 16x2 LCD, and in addition to that parallel interface, it also supports I2C and SPI interfaces. The resolution, as we already know, is 128x64, which gives us a decent amount of detail for many embedded applications. For the power supply, the IC logic operates within a voltage range that most MCUs can directly supply. However, for actually driving the panel LEDs, we need a boosted voltage, typically generated internally using a charge pump, and we will talk about that too. Alright, that covers the quick intro about this controller chip. You can always give the datasheet a read if you want even deeper details. Now let's move on to the main block diagram. Starting from the extreme left side, the first block we encounter is the MCU interface, which includes all the necessary inputs which are needed to display our pixels. Depending on the interface mode you choose, parallel or serial, different pins will be used. Let's focus on SPI, since that is what we will be using. Pins like E and RW are not needed in serial mode. The BS2, BS1 and BS0 pins decide the interface mode and are usually configured on the board itself. We will talk about them shortly. In SPI, D0 acts as the SPI clock and D1 as SPI MOSI, master out, slave in, data pin. Pins D2 to D7 are not needed for SPI operation. Below the MCU interface block, you will find the command decoder. This block is active when a command is sent from the MCU to the display. Commands allow you to control things like the oscillator frequency, which affects refresh rate or frame rate, and the contrast level, which in turn affects the display quality and power consumption. On the power supply side, we have VDD for logic and VCC for driving the OLED panel itself. Moving on, connected to the MCU interface on the right, we have GDD RAM or Graphic Display Data RAM. When the MCU sends data instead of a command, it gets stored here. An important point to note: data gets stored in RAM while commands eventually get stored in internal registers. The GDD RAM holds 1 bit per pixel, representing whether that pixel is on or off. Now, with a resolution of 128x64, that gives us 8192 bits, which is 1024 bytes or 1 kilobyte of memory space. Pretty compact, huh? Once we have all our pixel data ready in GDD RAM, it is passed to the display controller block, which then controls the segment and common drivers. These drivers activate the correct LEDs to form the image on the panel. And that, in short, is our block diagram walkthrough. If this feels like a lot to absorb, no worries. You can always pause here, clear your mind for a moment, and then jump back in whenever you are ready. Moving on, we come to the chip pad assignment and size details in the datasheet. This chip actually comes in two packaging options: COG, which stands for chip on glass, and COF, which stands for chip on film. In display terminology, COG refers to when the IC is mounted directly on the glass and takes up some area on the display panel itself. This means that the active screen area is slightly smaller than the total glass panel size, because part of it is occupied by the chip. On the other hand, COF means the IC is shifted onto the flexible ribbon or flex cable. This allows the entire glass panel to be used as the active display area, giving you a true edge-to-edge or full-size screen. If you are curious, you can definitely read more about the packaging technologies in display design resources. But for now, let's focus on the SSD1306. The part number SSD1306Z refers to the COG package with 128 segment drivers and 64 common drivers. There is also SSD1306TR1, which uses the COF package. Scrolling down, we find the pin description table, where you can read about what each pin does and what it's actually responsible for. Remember, we talked about BS0, BS1 and BS2 pins earlier? Yes, these are bus selection pins. And in our case, since we are using the 4-wire serial interface or SPI, all of them are connected to ground. Now you might be wondering, why 4-wire serial and not 3-wire? Why? We will get to that in just a moment. Here you can see a table that summarizes each pin relative to the selected bus interface, which data pins or control signals are needed in each case. Since we will be using a reset signal, a data command pin, a chip select pin, yes, for the 7-pin variant module, not the 6-pin one, a SPI clock on D0, and SPI MOSI on D1. We will go with the 4-wire SPI interface. Moving on, in this setup, D2 should be left unconnected, D3 to D7 should be connected to ground. To write a command, the DC pin should be held low, and to write a data, it should be pulled high. The CS pin needs to be pulled low to activate a specific SPI transaction. Then, depending on whether you have selected command or data, SPI data gets sent to the appropriate location inside the chip, as we discussed earlier. Finally, in this section of the datasheet, you can see the right execution diagram for SPI mode, which shows exactly how control signals flow during communication. Alright, quick recap. So far, SSD1306Z is a COG package chip for our OLED with serial parallel interface. Each interface requires certain pins and execution flow pattern, which allows MCU to send data or command. Command control display features. Image data is sent to GDDRAM, which then controls segment and common drivers to display pixels. Alright, let's talk about the oscillator clock frequency and the display clock. In our case, we are using the internal oscillator built into this controller. To generate the main clock, we can adjust this using command D5. If you look closely at this command, we will find that the upper nibble, or bits 7 to 4, controls the oscillator frequency. By default, its value is set to 8. This oscillator frequency FOSC is then passed through a clock divider block to generate the final display clock DCLK. This divider is also set through the same D5 command, but this time using the lower nibble bits 3 to 0, with the default value set to 0, meaning the divide ratio is 0 plus 1 equal to 1, and it can be anything up to 16. Finally, the frame frequency of the display is calculated using this formula right here, where D is the clock division ratio that has been set to 1. K is set to 54 by default. Mux set to 64 in this case. Now, we know all the values except for the exact oscillator frequency in Hertz. If we scroll down to the AC characteristics section in this datasheet, we see that FOSC ranges from 333 kHz to 407 kHz with a typical value of 370 kHz. But it's important to note that this typical value is specified at a logic voltage of 2.8 volt. So This might be slightly different when we are using a 3v3 supply, usually a bit higher in practice. But for now, let's assume the typical FOSC value of 370 kHz. When we plug that into our formula, we end up with a frame frequency of around 107 Hz. This means the OLED display refreshes its screen 107 times per second, or more precisely, the display controller fetches the GDDRAM data 107 times every second to update the pixels. Then we have the segment and common drivers. Basically, there are 128 columns or segments, and each of them has its own current source that drives the LED pixels for any given row out of the 64 commons. The segment current can be adjusted up to 100 microamps depending on the brightness and contrast settings. If we look at the phase-wise waveform of segment driving, it happens in 3 steps, where the pixel is first discharged, then charged with new data, and finally the image is driven. This cycle repeats continuously to refresh the display. Next, let's talk about GDDRAM a bit, a name that has been popping up quite a bit so far. This memory space is where all the pixel data for our 128x64 display is stored. Now this space is further divided into 8 pages, which are numbered from 0 to 7. From the resolution, we know that we have 128 columns and 64 rows. If we divide 64 rows by 8, we get 8 rows per page. When we send SPI data to this display controller from our MCU, the data is written column by column, page by page. Within each page, the bits of each byte of SPI data represent pixels vertically. That is, D0 of our data corresponds to the top row in that page, and D7 bit corresponds to the bottom row of that particular page. You can also see this clearly in the diagram which is shown here. The segment related current, or ISEG, is actually dependent on the level of contrast we select for the display. It also relies on a reference current called IREF, which is set using an external resistor. Yes, a simple passive component. If more pixels in a column are turned on at a given time, the total segment current required is higher. In short, the more pixels you light, the more current the driver needs to supply. Following this, we have a list of all the commands supported by this controller. You can definitely go through each one in detail, but since we have limited time, we won't be discussing all of them right now. So let's jump directly to the command description section and talk about an interesting topic, memory addressing modes. First, we have page addressing mode. In this mode, let's say we write our first data byte at column 0, page 0. Once this byte is written, the column pointer automatically increments by 1, moving to column 1. So the next data byte can be placed there. This continues until we reach column 127, at which point the column pointer resets back to column 0. Now, to move to the next page, we need to manually set the page address and repeat the process. There's a figure in the datasheet that shows this clearly. You first send a page select command B0 to B7. Then you set lower column address anywhere between 0x00 to 0x0f, and finally the upper column address between 0x10 to 0x1f. For example, B2, 03 and 10 together put us at segment 3 of page 2. Similarly, there are also horizontal and vertical addressing modes where the pointers automatically advance and wrap around. We won't go into detail here since most common usage is page addressing. The datasheet is absolutely loaded with information, and you will definitely need to put in some effort from your end as well, since not everything can be covered in a single video. So let's quickly scroll along and wrap up our discussion. Towards the end of our datasheet, there's a dedicated section on the charge pump regulator. It mentions that with just 2 additional capacitors, we can generate roughly a voltage above 7 volts to drive our OLED display block, even if we are supplying only 3v3 logic from our MCU. Of course, there's a command to enable this feature as well. To turn on the charge pump, we need to send 0hex 8D followed by 0hex 14 before finally turning the display on. But don't worry, we will be examining these settings in much detail in our upcoming video. Now, let's talk a bit about our OLED display module schematic. Remember our earlier discussion about the BS2, BS1 and BS0 pins that control the bus selection? Yes, in this schematic, we can clearly see a few resistors that let us choose between I2C and 3 or 4 wire SPI modes. By default, our board supports 4 wire SPI, so resistors R3 and R4 are connected to ground, pulling BS0 and BS1 low. BS2 is already grounded as well. Also, R8 is not populated. That leaves D2 unconnected, while D3 to D7 are pulled low. This matches exactly what we saw in the datasheet. If we want to switch to 3-wire SPI, we need to make R2 and R3 active. In this configuration, BS0 gets pulled high while BS1 remains low. For I2C mode, R1 and R4 needs to be active. This pulls BS1 high and BS0 low. Additionally, R6 and R7 act as pull-up resistors for the I2C, SDA and SCL lines. R8 is required to connect the D2 SDA out pin to the shared SDA line D1. You can always refer back to the datasheets table to clarify these configurations if needed. We also have capacitors C3 and C4 which serve as the charge pump capacitors, exactly like we discussed at the end of the datasheet. Pins E and RW are tied to ground in this design. There's also a voltage regulator labeled U2 that converts the input supply to the logic voltage needed by the IC. I couldn't find the exact part number, but based on an article from Vivonomicon about DIY display modules, it's likely similar to an AP2210, which outputs 3v3. Finally, for the reference current, there's a 910 kilo ohm resistor included in the design. I'll also include the article link in the video description if you'd like to dive deeper. Designing the board isn't too difficult, but the real challenge is soldering the thin display pads carefully. So handle it with extra care. Alright, so that's it for this video. I know it turned out a bit longer, but I really hope you gained something valuable out of it. In this video, we learned how the SSD1306 works internally, how it handles commands and pixel data, and how it drives each segment and command line. We also discussed the actual hardware module and practical details that you will need for your projects. In the next video, we will put all this knowledge into action with a full coding walkthrough to get your display up and running. See you there. Do not forget to like and share this video, and do subscribe for such amazing contents. This is Avinashi Tech signing off.